apologize for having the timing a little off, but this other event going on now, and then also the World Series. So I'm going to try and keep the Giants game open in the corner, so that people can at least get a read out of what's going on.
You get like the Warriors game with Hopper as well.
Which happens in that.
Right.
They'll play again tomorrow.
Season?
Really? Already?
And so by now, I hope you guys have all seen this slide presentation I made. It's essentially going to be the entire book and all the course stuff for the entire class. I'm not really expecting to add anything to it as we go, but we'll talk through the examples and things like that. But all the material that I'm planning on covering is generally up in there. The details, of course, we can expand on. So, let's just get started. Okay, cool. So, you all know me, I'm Brian. I'm a neuroscience grad student. I'm a 6th-year student. This past summer, I did an internship at Google, and after that, I went through the rest of the interview process, and they offered me a job, and I'll be taking that and going to work there next year. So, why I wanted to do this is that for that, I went back and did a bunch of review of the basic computer science things that we don't have to study as neuroscientists or other researchers. Because for the most part, we don't worry about the nitty-gritty details of runtime complexities and things like that. But it's important for companies, because if you're running this on 1 million computers and you're paying money for each one of those, you want that to be as efficient as possible. Because if you save 1% of your computing time, you can save $1 billion a year, or more. And so it's worth, that's why they focus on these things. And so some of this, or most of this will not help you with your research at all, but it'll give you kind of a different way of thinking about the types of questions that are out there. And so my thought right now, and this will be probably changing over time, is it'll take about 4 sessions to kind of cover all the material in these classes. For the most part, though, they'll just cover the concepts. And if you want to test yourself and do things like that, you'll need to work a little bit on your own, and we can have a couple of extra classes at the end of that to talk through some examples and work through them as a group. For the code in this, I'm using Python, in part because it's one of the kind of standard Google programming languages, which MATLAB is not. MATLAB is pretty much not anywhere. So if you want to do an interview at some company, you can probably do it with Python. It's hard to do it with MATLAB. I'm not going to talk about advanced topics like machine learning or neural networks or anything like that. They're interesting. They're generally not required to get a job anywhere. Usually what you need to do is you need to prove that you have basic computer science skills, and you can learn whatever skills you need to pick up then in the future. But for the most part, you just need to prove that you have a good basic skill set. So that's what we're going to cover. The interview process I'm just going to talk through really quickly, because all this information is available online from Google's websites and things like that. You'll typically do 2 to 4 phone interviews when you send out your resume and things like that. Then if you're doing an internship, which I recommend, it's a good way to kind of get a feel for the company, figuring out if you actually enjoy this type of work. And it's also a really good way to network. The internship itself is pretty easy. You just kind of do work, which we're all used to doing. We're all used to working very hard. So that part's relatively easy. I believe once you've gotten your PhD, you can no longer do an internship. But you don't have to do it during any particular time of the calendar year. You can kind of move that around. After the internship, you would have to do 2 interviews in person. If you do not do an internship, you have to do 5 interviews. And those are on a whiteboard, which is really hard to write code on. And so if you're going to do that, make sure you spend a lot of time actually practicing on a whiteboard, writing things out, because it's annoying. And then check your work afterwards, which is hard to do. And then just for the interest, you then sign your paperwork saying you signed up and you get hired. And then about a month or two before you actually get started, you figure out what team you're going to be working for. Yeah.
Is there a reason why they're supposed to do it on the whiteboard? And then, like, do they have a logic behind that?
Part is to make it awkward. A part is that it's a limiting constraint then. Like the amount of time that it takes you to write something clearly on a whiteboard is a lot longer than it takes you to type it. And so it forces you to take your time and do things correctly the first time. And so part of these kind of time pressures that you won't have in the real world, and so they accept answers for your work on the whiteboard that you would never use in practice. A large part of it is you just need to get something that works on the whiteboard, and then you talk through how you would make it better, how would you make it optimal, how would you get a more efficient design of it. And we can talk through some examples of that a little bit later on. But often I think a lot of it is also just historical. It's always kind of been you do a whiteboard interview for your in-person interview. So they just kept that.
So what do they ask you in a technical interview?
They ask you about the things we're about to talk about. So it's a lot of kind of basic algorithms and basic data structures, and then applications of that. So they usually give you a short problem that they can kind of describe in words in less than a minute, and then you have to write out the code that would produce a solution to that problem.
Okay. How about during a phone technical interview?
It's actually almost exactly the same. They ask slightly easier questions, perhaps, or maybe they're, depending on what you're exactly interviewing for, they might allow easier answers or give you more leeway. In part, it's a lot easier to type, so you have more time, which also makes it a more relaxed environment. But it's generally speaking the same types of questions.
Is everything in pseudocode, or is it in a particular language?
Everything is a language that you choose, but at Google, at least, the three kind of main ones that they encourage you to interview in are Python, Java, and C++. If you're going to a different company, look up what their preferred one is. I think at Google they would allow you more leeway technically, but they kind of give you a look while they did it, I imagine. And so, at the same time, you don't need to know any of these languages like in particularly amazing detail. So you don't need to know like really kind of intricate nitty-gritty details about how they work. You just need to be able to program in them comfortably. And so, always choose what you're most comfortable with, because that's what's going to show through. They're not going to worry too much if you need to ask, like, what is function X? I know there's a function that does this, I just can't remember what it's called. Don't worry about that as much, more worry about like, the comfort in actually designing an algorithm. But they want it to be real code as opposed to pseudocode, just to make sure that you really know what you're doing. So the topics that we'll talk about are what you would need for doing these interview problems. It's kind of something called Big O notation, which is kind of analyzing how complex a piece of code is. And so we'll talk about this for the rest of the day, so I'm going to skip for now. Then in most of the later classes, we'll talk about data structures, and so how you hold data in memory or in a computer or save it to a disk so you can access it efficiently. We'll talk about algorithms then that allow you to search through some of these data structures or kind of explore space, some of the differences between them. Then we'll also talk about some general purpose ideas about how computers work and how they're currently programmed for the most part. And most of these will be on later classes. Generally, I'm going to encourage you in the examples that I gave you are all in Python. Coming from the background of mostly programming in MATLAB, Python is the easiest of the accepted Google programming languages to use. It's also a scripting language. It's nice in a lot of ways. Has its fair share of problems, as all things do, but it's pretty good to work with. One thing is that I'll encourage you to use Wakari.io, which is this website that basically lets you run something called IPython, which is a Python interpreter that has some other positive things about it. So you can actually go and run Python in your web browser. And it stores kind of a copy of everything you've done. And so it's a really nice environment for just getting work done and exploring. And I encourage you to use it.
Isn't that what IPython is?
Pardon?
Isn't that what IPython is itself? Like, can't you?
Yeah. And so this is just something that runs it in the cloud. So you don't have to install it on your computer and you don't have to worry about, oh no, I changed computers. I don't have that file. So it's something to use while I'm doing experiments. If I have a little bit of free time, I can open it up from any computer and get a little practice in or get a little work
Can you
done.
install dependencies on here? Or if you're limited to whatever packages you have?
Yeah, there are some ways to do it. For most of the things that you'll need to practice for doing interviews,
Right.
you don't need any dependencies.
Right.
So I haven't tried installing dependencies. I believe there's a way to do it. I don't know what the restrictions are. They have a lot of kind of basic things, like the entire scientific Python stack is already on there.
Yeah.
But if you kind of build a custom package, I at least am unaware how you get that up there. But it is possible. I just don't know if it costs money or not. And so, yeah. So I've already made a IPython notebook with kind of all the answers for all the different types of questions that we'll be going over, and all the different types of data structures, algorithms, and such. There are links to them. You can find it on GitHub or just view it directly. If you want other things to do, want to kind of give yourself a bit of a challenge, it's a website called TalkCoder, and there's a couple of others that just host computer science challenges. And they have, normally you go and take these in person, you're timed, but they keep a log of all the ones that have been kind of used recently, produced recently. So you can go and find a question there, work through it, and test yourself that way. And that's probably the best way to prepare for the interviews. You get a short question, you have to program an answer. And this one's nice because it gives you example outputs, or examples of input and output, so you can test if your code is actually working. And then go through and use Wikipedia for the answers. Wikipedia actually has a pretty well-maintained section for most computer science topics, and so you can actually get a long ways doing that. If you're interested in more data type things, like data science or data engineering is the new one, check out the data or the Insight Fellowships. They're really cool. I know a number of people have done them and had very good results. So take a look at them. And so we're going to start by talking today about, well, sorry, any questions on anything in the introduction so far? Awesome. So we're going to talk today about big O notation. And all that really is referring to is kind of a shorthand term, and is often called big O notation because you describe it by putting it, or write it down by putting a capital O, some parentheses, and some description inside. And that description is how long does it take this code to run? What happens when you kind of run a sorting algorithm on a list of 10 elements? How does that change when you then run the same sorting algorithm on a list of 1 million elements, 10 million? How does the size of what you're trying to do influence how your algorithm runs? Because that's what this kind of complexity idea is. And generally speaking, for big O notation, what you often talk about is talk about the biggest term. So if you have something that's like quadratic, so it's n squared, if you have 1 million elements, what's going to dominate is that squared term. If you have like 3 times n or like some plus 1,000, that's not going to matter because you have 1 million things. So often people will talk about and focus on is kind of the largest, the highest order term. At the same time, when you actually go and do your interviews, Google as a company actually has to deal with a whole range of things. And so you actually need to be aware of kind of the low level, kind of nitty-gritty of how kind of constant terms interact as well. And so we'll talk through all this. It'll make more sense as we go through examples of it, but it's something to be aware of. And so a couple examples is that you have a list of things that are kind of completely out of order, and you want to get the maximum number in a list of 100 items. If to be guaranteed that you found the maximum item, what's the minimum number of items you have to look through?
All of them.
All of them, yeah. You have to look through each one at least once to know that it's not the largest or that it is the largest. And so this is going to be something that's an order and an operation. And so if instead you want to do every pairwise comparison, let's say you have 2 sets of spike trains, you want to do cross correlations or something, or correlation between multiple things. Every pairwise comparison grows order n squared. Because for every object in your list, you have to do n actions for it. And so it becomes n times n. My hand signals weren't very good. And it ends up kind of forming this square. And so that'll grow as n squared. And so if you have like 1 item in each, they'll run the same amount of time. But as you get to 100 items in one, The linear one is growing very slowly. And polynomial one will grow much faster. And so we'll talk through some of the basic cases. Right now, this probably isn't going to make a lot of sense. You've seen some of these topics before. These are just kind of give you an idea of what the major categories are that come up. And we'll see where these fall into place and where they actually happen in code and in real use coming up in a little bit. Probably in the next class, or definitely at least in the next class. So one is the best case, which is called constant time. Anything you want to do, I can tell you exactly how long it will take to give you an answer. It doesn't matter if you have one item in there or if you have 100 million items in there. You always get the answer in exactly constant amount of time. And so that's what you really want, because you can never really do better than that. As saying, I want something, you get it back immediately. You can do things that are kind of the next general step from there is that they grow logarithmically. So they grow a little bit, they don't grow linearly, they grow slower than that. And so if you have, is this on the board graphs? So if you have something that was constant time, it will always take the same amount of time. This is number of items. This is time. Constant time means that no matter how many items you have, it will grow slowly. If you have something that's logarithmic, it levels off. So that every time you add more items, you need to add more and more items for it to really make a difference. And so this is a pretty good case. This is often optimal algorithms for whole hosts of problems. We'll talk through them in a bit as more examples. Then you can do things that are linear in time. And this is that example we talked about where if you had to search through every item in the list, that's what you could find something as. And so it's kind of a useful base place. And this is kind of the difference between using a simple algorithm like saying, hey, I'm just going to search through the list until I find the biggest one. And saying, well, I'm going to do something to have a better trick. To be like, I'm going to make my list partially sorted or use some sort of sorting algorithm to be able to find items a little bit more easily. So usually when you move between the classes, you have some better trick for your algorithm, and just make your life easier. There are things like sorting algorithms that are between, eventually you get to things that are n squared, and all of these can be the right things to do at different points in time. Kind of the worst case complexity that it's hard to get worse than is factorial, because that goes up really fast. If you have to do a factorial number of operations for every item that gets added, you're doing a lot of brute force, like I'm just going to test every possible combination or permutation of these items, and eventually I'll find the right one. If you write this code during a coding interview, that's okay, as long as you tell them why you did a terrible job. Because for an interview they want to know, can you write code? But they also want to know, can you think about it? So because you're limited in the amount of time you have to write on a whiteboard or to talk them through something, you need to give them an answer. And they want to see an answer that works. And brute force algorithms work. We also need to then talk about how you would make it better. And that's part of what it is. It's both having the ability to spit something out on demand, but then be able to think about it and say, okay, I could make this better than the first thing that popped into my head. And so you can kind of talk through this while you're actually doing your work. And say like, okay, I did this algorithm that has these problems, here's how you can improve it. And they're fine with that, generally speaking. But it's acceptable in an interview. So that's often a good place to focus on, and make sure you can at least always do that. From experience, I can say it works. So all this, it's going to make more sense after we do some algorithms. And as we start going through these, you'll want to think about what the complexity is. So how hard is something to do? If you make your own algorithm, how are you actually doing? How many operations does it take to sort a list? Like find the next item in a sorted list versus a non-sorted list. How can you sort things? And so check your answers on Wikipedia, they'll all be there. There's all kinds of conditions that you can expand on the basic stuff we're going to be covering. If you start deleting items, what does that do? We'll talk about some of them. Think about them on your own. And with that, I think we're done on this topic. So does anybody have any questions? Awesome. moving on through. And so we'll see how time goes for today. We're doing well. But the things I wanted to talk about are now starting to get into data structures. And so this is how we store data on a computer, which is something, most of you come from a MATLAB background, you probably haven't had to think about too much. Probably done a little bit, but the first kind of question is, how are you actually accessing your data? And in scripting languages, it's usually not an issue, but you still need to know what the ideas are for this next set of topics. So we're going to talk about two different cases. One are the actual values themselves, and the other is references. And so if you have a piece of data, like let's say it's some like giant array of stuff, and like you need to store every value in that array. And like that's important because you want to say, I know all the values in this array, so I have this giant list. And those numbers need to exist somewhere. No matter what, you know where they need to be. You know that they need to be somewhere so you can look them up later, you can mess with them, play with them, study them. And that takes up space. But what if you just want to say like, well, I know I have this list in memory somewhere, but I don't want to make like an entire another copy of it. I just want to know that I can get back to it somewhere. And so that's called storing a reference. And so these kind of point at locations in memory. They store addresses, and so this is the big difference between a 32-bit computer and a 64-bit computer. You probably didn't need to know this ever before, and you probably will never need to go per se again. But they store different amounts of memory for their addresses. And this allows you to reference different amounts of things. And it's nice because if you have like say a 10 megabyte array of data or something, some object that's like 10 megabytes in size. If you want to give it to a function, you might have to copy all of those 10 megabytes or gigabytes of data just to make that copy. And every time you make a function call, you'd have to do that entire bit of work, which is a giant waste of time if you're not changing anything. And so this is where references come in. They let you kind of access something as just an address. So it's kind of like thinking in, well, a little bit of an address. Thinking in terms of like on a map, you have houses that take up physical space. Every house has an address. I mean, at a particular address, you might have a building the size of this one, or you might have a small apartment. And the reference will always take the same amount of space, but the actual amount of space taken up by that value could be different. And you'll always have to have the data value stored somewhere, but you can use different amounts of space, or you can use less space and use references. This will kind of come up when we're talking about different data structures, because they often need to, we won't talk too much about the value of the data they store. We're mostly going to be talking about how they relate to other objects. This kind of distinction is something that will hopefully become more apparent as we talk about this next piece of data, or this next data structure, which is a linked list. It's pretty much the simplest data structure, just about the simplest data structure you can imagine. You're going to say, I have an item. And I would generally call my general purpose thing an item, except when I call it a name. And we're going to have the first item in the list. It's going to have two things. It's going to have some data value, which is important. This is why you actually have a list. It is the thing you're actually trying to store. At the same time, we're not going to talk about it at all for the rest of the class because we assume that you have some reason for storing this piece of data, and that's important to you. As a programmer, I can't predict what you need to store, so I don't know what you're going to put there. What I can say, though, is if I have a list of one item isn't very useful. So that means that there needs to be another item over here, which will also have some data. But if I know where the first item is in the list, I need something that tells me where the next item is. And so this is where you store a reference, because you don't want to store this entire copy as some new piece of data here, because you don't know how many nested, how long this list should be, storing nested and nested and nested copies. All you can do is say that there's a reference to the next item in the list. And so this just goes and points over here and says, aha, there's something that's behind this one. There's something in this order. And then the same thing, this one will similarly store a reference to the next item in the list. And you can do that for as long as you want. If you want to know. Yeah.
Is this what lists in Python do?
Truthfully, I can't recall. I think my guess is that they are actually dynamically expanding arrays of references. And so it's a little bit kind of an in-between object. For the purposes of the assignments, or the kind of examples, you can use lists to mimic one of these, or kind of anything else. I don't believe that Python uses these for lists. And what might be some of the kind of issues with using a linked list as a data structure? So now we're just going to, now we've talked about this. Well, first of all, does everybody understand this? Okay. So what are some problems with it?
How do you get to the last item?
Good question. So how long would it take to get to the last item? Okay. So that's exactly the perfect way to answer that question. So it'd be an order n operation to go through the list and find the last item. And so a linked list is great if you want to know something at the front. What's the way kind of around that problem?
No, how long the list is, so that you can.
Okay, well, so let's say we know how long the list is. We know that the list has 24 elements in it. How will that help you figure out or get to the 24th item?
Does this, I mean, so I guess I'm in this paradigm, I'm not sure how you would access that. Because I mean, if it's like, that's why I asked my question, if it's like a list in Python, then you can just, knowing that, like, the length of it, allows you to access it directly.
Yeah,
So,
okay. So it is, in that sense, it is not like it's not like a list in Python.
so it has to follow some flow.
Yep. So your program has this thing you call a root. This is the first node in the list that you are aware of. And so you have this root pointer in your program. Your program doesn't know anything about this. All it can do is follow this root pointer that points to the first item. So, sorry, that's a good clarification. So now that we know about this, how might we, what could be useful if we wanted to get to the last item in the list? It's like a really stupid way.
Storing the one before it?
Storing the one before it, yeah. Or, if you only wanted the last item,
It's the last one.
yeah, exactly. So you can say, well, you know, we have a root pointer, well, let's keep a last pointer. You know, sometimes that's a good thing to do. If you know that all you're going to be doing is, you know, you quickly want to be able to get the first item on the list, but you still want to be able to put stuff on the end. How hard would it be to put something on the end if you already have a pointer to the last item? So, sorry, a pointer is a name for a reference. Sorry, I'm switching between terminology there. I apologize. So all it is saying, you know, there is this mysterious item somewhere out there. And that item, you know, has data associated with it. We don't care about it right now. But it also has a reference to where to go else, where the next item is in the list.
And what initially sets up the order of things.
Often the order that they were added. You could do things where you could sort them, put them in any order you want. Often in terms of talking about these problems, it's not specified how this list got created. Somebody might have created it in like a perfect way, they might have given them all to you in order to begin with. Or they might have just thrown them in there randomly. They also, in some cases, might have then figured out how your algorithm works and specifically gone and put them in the worst possible order for your algorithm. And you need to be, and we'll talk through examples where that matters, and why that matters.
What are these lists used? Like, what are they used for?
That's a good question. Well, so what can we describe about this list? Like, what's easy to do with this list?
Go through things in order.
Go through things in order. Perfect example. So if you want to do some like big long operation on a list of items, you can step through and take the first one and say, I have the first one, I'm going to process it a long time. Go and take the second one, I'm going to process it a long time. You can take them in order. It's a great thing to do.
Yeah, things in the middle.
You can add things in the middle. So we'll talk about why that's a cool thing.
What does that mean? You have to like add a point? I don't quite understand.
Yeah, well, so let's talk through. What would it mean to add something at, I'm going to draw out one more backup. I'm gonna drop both.
Yeah,
Yep.
you get like move a reference.
And so, yeah. So what would it take to add something in at between position 2 and 3?
We just change the second reference to something else.
Yeah. So I'm going to even like go even unfortunately back a step. Because we're starting out over here in our program. So from our program's perspective, like way back here, what do we have to do to get to being able to add something? Yeah. You have to go to the next one. You have to go to the next one. And now you can say, aha, I have two things. I have the one that I'm currently at, and I know where I'm supposed to go next. And so we want to add one, so that's a new one here. And now we have this new one that we want to put in there. So what, you think you guys have said it again, so we can say it again one more time. What do I have to do to get this guy in here?
Change the reference
Which reference?
on number 2.
Okay.
Remove the reference from number 2. And then
Yep.
change the reference in number 2 to go into the new one.
That is correct. And that's a great answer. Because if you, the first thing you do is you just say, aha, I'm going to set this guy down here. If you just make that change, you've lost the end of your list. And so it's one of these unfortunate situations that's just incredibly nitpicky, where you just need to remember, hey, I need to make sure I don't lose anything. So you set these ones to both point to the same thing, and then you got to move this guy over. Point down here. And unfortunately, the fact that you need to keep track of things you're moving around is part of why algorithms often take a long time to run. And so it's a small but important detail. You need to keep track of the things you don't want to forget.
So, if I can just take a step back for a second.
Yeah.
From what little of, for example, Python that I know, I can't really think of a particular structure or data storage mechanism in Python that appears to use something like this. For example, lists don't, at least in the superficial level, seem to use this process. And so, are we supposed to be thinking of this in more of an abstract way of implementing an algorithm, or literally like a structure that stores data in a modern programming language?
Both.
Okay.
So we're going to talk about them in going through the class. They'll be abstract for the most part. But I encourage you to look through the examples that I've actually written in the code.
I think this is how MATLAB Stellar is written.
Really?
I think so. It has to be, right?
They do references, and so they're similar to lists, where it's, I'll go through this at the end of class. No, actually. So we were talking about this difference between data being data itself or having references. And we use this as an opportunity to skip ahead just a little bit, because there's another very simple data structure that you're all pretty familiar with, which is an array. And so an array is exactly what you think of it as. It's a bunch of stuff that's literally right next to each other that holds your data. This would be an example of a 4-item array. And it's really nice because you can say, I want the 4th item, and you jump to the 4th location and pick it up. But how do you know where the 4th item is? Like, how would you know where the 4th item is? If you're just going to like jump to some location, how do you know how far to jump?
I have no idea.
It's all blocked off together.
Yeah, it's all blocked off together. So this is one kind of contiguous piece of memory. And so you know that like everything you want is connected. But how far should you go in this connected block of stuff? Like if you want the 1st item, what do? You just look, and so you have some, your array has some, say, root pointer. It points to where the 1st element is, the program does. If you want the 1st item in here, what do? Where would you look? Yeah, you look where your root pointer is. What if you want the 2nd item?
Root pointer plus whatever the size of the block is.
Exactly. And so that's the thing. There's a fixed size block.
What is a block?
Good question. So a block is whatever data value you're storing.
Was it the cell, or is it like how much of something it takes up?
It's how much space it takes up. And so if you have, let's say, an integer in here, so it's just one small number, let's say a bit, either a 0 or a 1. This guy is exactly 1 bit away from this guy. It's exactly 1 bit away from this guy. And so you can jump to the 4th bit really easily. But let's say that they're like 32-bit integers. Then you'd say, okay, well, if they're all 32-bit integers, I know that this guy is it's 128 away. And so you could just kind of jump that far, and you would know where exactly it is. The problem with that, though, is that if this guy's an integer, and this guy's a bit, all of a sudden you don't know where they are. You can no longer tell what the predicted position of something should be if they're all different sizes. And so you either have to do two things in that. So is that making sense to people?
So, is that actually how MATLAB works? Like if you want to access, if let's say you have an array that's like 1 billion items long, does it actually take longer to access the 1,000,000th item as compared to the first?
That's how a linked list works. It would take longer. For this, because you can predict where something is, it doesn't take any extra time. Because you just do the math to say, well, 1 billion times the size of my data is how far I jump.
I was saying like in a case where each item is not an uniform shape.
Yeah, and so how might you get around that issue?
Just give it some pseudo address that is a measure or something.
Perfect. And so if we go back to all the references have a fixed size. Every reference is a fixed size. So all these pointers are a fixed size. And so the way a cell array works in MATLAB or the way a array list works in Java is they don't actually store your data directly. What each one of them stores is a reference. So this is how Python lists work, and essentially all of Python works actually. It's each one stores a reference. And that's handy because in this thing you can store the number 12, you can store a single bit, you can store a string. And because all you're storing are memory addresses that are all the same size, you can go anywhere and you can know that the 1,000th item in your cell array is at this location, because you have to do 2 jumps then. One to get to that pointer, or that reference, and then another one to take that reference to whatever it's storing. And so that's how a cell array works in MATLAB. Is it still has this fixed size cost for all of the references, but then it has this additional step where you have to then take that reference to go to another location to get the actual data value from it. But what if what you're trying to store is bits, 1s and 0s? Which of these is more efficient? Using this kind of...
Not using the reference, because it's not necessary.
Exactly. So this reference is always going to be 32 or 64 bits. But if your data is smaller than that, and oftentimes our data is, this is not going to be helpful. You're going to be wasting a ton of space.
Well, though not only does it have to be smaller than that, it has to be consistent. Right?
Yes.
Like you couldn't, there was something between 1 bit and 64 bits in like a range, and then if you had things that were ranging inside, even though they were lower than 64 bits.
Yeah, so that's one thing. You can store, let's say you use 16-bit integers. You can store 0s and 1s in 16-bit integers. It's totally fine. You can store like mostly 0s and 1s and sometimes an 8 in 16-bit integers. It's just kind of how much additional space are you wasting.
Oh, I see.
And so that's kind of a question. I mean, if you're trying to
You
do
could
this,
convert something to be the right size. Fit the structure.
yes, yeah, you can convert between things, and Python doesn't really have a way of doing it. Java does too. Java does. I think actually Python does. You can cast things. You can do what's called casting something. You can say like, oh, this piece of data, it's a 12, but I'm going to pretend it's no longer a number. I'm going to pretend it's a character. And I'm going to pull out the character that has the same pattern of bits as the number 12. And so, because computers only store 0s and 1s, you can always point to some address with a reference, and you can pretend anything you want is there. It's bad. It produces a ton of problems. And this is where most bugs come from in or this is where many bugs come from code, is you're somehow get away from where you were thought you were looking, and you overwrite some value because you pretended what you knew was there. When that happens, you destroy your code. If that's a major problem, that actually can happen. And operating systems try and prevent you from doing that. Yeah. Example 1, example 2. So let's go through the same example though, and say we have a list with 4 items in this case. What happens if we want to add something between item 2 and item 3? What do we have to do? What are some steps?
Well, they just want to jump, like, you know, like how far you have to jump to get to the item between the two, I guess.
So
Like
it's-
item 3.
Yeah, so we can get to item 3, and we can get to item 2. Where's that got us? In and out, right? So we have like 4 buckets in a row.
You want to get between,
How do you get between 2 buckets?
you go half distances.
Okay, and so you're at half a distance. There's no bucket there.
And then create something.
How do you create buckets? You make a whole new list. So you have to make a whole new array. And so if you try to put something in the middle, you have to move everything else down buckets. There's only like a fixed amount of space. So you actually have to say, well, you know, these 2 get copied down into some space. And you make a new bucket. And you have to copy everything over into some new space just so you have a blank bucket for you to use.
So you want to initialize those.
Yeah. So this is why one reason MATLAB always says, oh, you're increasing the size of this variable every time you go through the loop. Please initialize this array so it'll run faster. This is exactly why. Because you have to make a new array every time you want to add something to the end, unless you initialize it at the proper size first.
So there's a point in the addition to MATLAB where it's using 2x memory. So if I basically if I have 8 gigs of memory, I have a contiguous block of 6, I can't add anything.
Potentially, yeah. Yeah. The temporary variables that get created can be large and double the size of your memory. And so that's why it's often important to say, like, you know what the size is going to be. If you get stuck in that, it's the best thing you can do. Otherwise, you do get this problem that, like, where else is that data going to go? If you want to put it in the middle, you need more space. How do you make more space? You can't just say, well, you know, give me a block of data over here, that's like completely unconnected. Because if you want to say, like, you know, I want the 5th position of this array, you're going to jump to here. And this is not anything your program is controlling. This is not where you want to be. This is not going to get you to this magical 5th element. And so you always need to kind of be aware of if this cost of copying these arrays is actually pretty big. Particularly, actually that's a good question. What would be the runtime complexity of copying this array? So we already talked about the space. It would take twice as much space to do. How long would it take to copy everything over? So, how long does it take to copy this guy over? First position.
Oh,
Yeah. So it takes 1 unit of time to copy the first one over. You then have to go through and copy every item. And so it takes n units of time. And so just doing this array copy, just add 1 single item, took the entire amount of space again, and also took the entire amount of time again. You have to go through the entire list just to add 1 item. And so this is one of the big issues that Peter may have known about in advance. If you want to add something to the middle of a list with a linked list, it's really easy. It might take you a little while to find the right spot to add it. And sometimes that's an issue, sometimes it's not though. But you can add something really easy, just change 1 pointer, 2 pointers. You're done. Here though, if you want to add something in the middle of the list, in this case we had to copy the entire list down to do a new space, which took additional space and additional time. And then we could find the outer item. And so this had what complexity? To add an item to the middle of the list here, if you already have this pointer. let's say we wanted to add something to the front. What complexity of time would that take? Order one, exactly, take a constant amount of time. You can just say, aha, I'm gonna put something here, I'm gonna fix my 2 reference pointers inside the front of the list. If you wanna add something to the front of this list, how long does it take? If you wanna like make a new,
Well, also
It's
Oh, oh,
it's
plus
not-
one.
yep, so it's gonna take order and time, because you had to make the list longer.
unless you have free contiguous memory next to it.
Things are usually don't let you expand things dynamically, but we could be in this case that we'll talk about where it's closer to it. So let's say we pre-assigned our list to be 6 places long, so we have some open spots. How does this change these problems that we were just talking about? Of adding things to this list, adding something to the front. Let's go with that.
It makes it so you could potentially drastically reduce your memory use,
Yep, because,
because you would need 2x memory to copy the list.
correct. So you wouldn't have to make a full new copy of the list. But what do you have to do?
To rewrite all of the values past that over previous.
Yep, so you still have to take order and time to move everything over by 1, just so you can add a new item in front of the list.
So does that mean it takes up less memory to add something to the empty spots?
So yeah, so if you want to add a new item to the end of the list, how long does that take? Yep, it's a constant operation. Because you just say, aha, I know where that's going to go, I put it in there, and we're done. And so arrays and this type of data structure is really good for doing that. It's really good for making manipulations, adding things to the end of the list, and you can find anything, any position of the list in constant time. Because you just say, I know it's the 4th item, you jump to where the 4th item would be, and you have it. But that's the kind of flip side, is there are some things it really sucks at doing, which is adding things to the middle of the list. Anytime you do that, it has a large cost. Sometimes that's the only way to make it work, and sometimes the ability to do is called random access, and this is where the random comes from the computer, is you can jump to any point in this array really easily, which is something you can't do, because you have to iterate through a linked list. But it's really hard to add things here, and it's really easy to add things here, if you know where you're at. And so these are the types of trade-offs that are going to come up again and again in class. It's like, well, under a lot of conditions, this is the best one you can have. This is what you want to do. There are also some conditions where there's this other thing that would normally be kind of stupid, that actually be a lot better. And so kind of being aware of these issues is kind of a good place to be. Because that's what we'll be hopefully going through a number of times as we go through the class. What's some other common operations to do with this?
How would you classify the time to take to put something in the middle of a linked list?
Let's walk through. So what are you thinking of? Can you tell me
It
what
was like
the
a million units long, you want to sometimes put it halfway through, sometimes a quarter through.
Okay, so to put something at the nth position in a linked list, and is all we have the root pointer?
Yep.
Well, let's work through the problem.
That way, if that n was the point of the list, it would just be O n.
Because,
With that one. And then rewrite the average before that.
in the new item, yeah. So to say that again, if you wanted to add something to the nth list, or the nth position, and all you had was this one, you would have to go through and walk all the n items, n-1 items, and then you could go and switch those. And switch the pointer to me. This one points to the next item, this next.
So that action there, does that also add to is it just n, or is it n plus something, or
Well, what would it be?
n plus 2, or
Perfect.
doing 2 things?
Yep, you do 2 things. You do 1, 2.
Isn't that still an, strictly speaking?
Well, loosely speaking, it's order n.
Well,
Strictly speaking, it's order n plus 2. And so this is
I thought
the,
that was the whole point behind big O, is that you intentionally ignore all the lower order.
this is what I caveat through in at the end, which is you have to do both. And so normally when we're kind of talking about it, you'll say it's an order n operation. And that's kind of the general thing to pay attention to. But somebody could get crafty and devise some situation where maybe these constant terms really add up. Maybe they end up being more than the kind of the n part under certain situations. Or maybe it's like a 2n versus something else. And sometimes that multiplied 2n could be bigger than an n squared.
That's what I get, like, in terms of constants, like if you say n plus 2, I mean, you're doing two things, but I mean, like, couldn't there be other situations where you're doing two things, but it takes more time to do those things?
Yeah. And so that's it's an issue that'll come up next class. That constant time can be.
It sounds like we're using arbitrary units that don't have meaning.
Yeah. So ideally, if you really go through it, since this is one of those things where it's the strictly versus loosely. In the loosely case, you just talk about what's the biggest term. And even if it was like 75n squared, you wouldn't even bother to say the 75. You just say it's n squared. And that's the loosely version of it. But there are times when, every operation matters. So if you wanted to be really careful, and we wanted to say, well, we want to like walk through this list of 75 numbers, it's actually not n plus 2. It's 2n plus 2. Because every time you take a step, you have to increment some counter value that counts how many steps you take. And so it's actually 2n plus 2 to get there. Because you have to say, well, I'm taking my first step, I'm following this point. Then you say, I decrement the value, so the number of steps I still have to take. And so then that's 2 for that one. And you have to take another step to follow the reference. And then decrement the value again. So that's 4. And so, strictly speaking, it's 2n plus 2.
So to just be completely pedantic,
Cool.
on average, it would actually be only that n over 2, because ahead of time you don't know which location you're going to want to insert it in. Sometimes it's the first, sometimes it's the last, and if it's uniformly distributed.
Well, unless you have somebody priori knowledge of the order of the list.
Yeah.
So, okay.
And so this is why another way that we can ask all these questions is not just, what's the complexity. You can say, what's the best? What's the average? And what's the worst? And so, for this example that we've been talking about, what would be the best case? How long would it take to run? Loosely speaking. 1. We have the front of the list. You just want to add an item at position 1. You take a constant amount of time to do that if you don't have to iterate through anything. So the best case would be 1. The average amount of time it takes. Because?
So isn't it n over 2?
Yeah, so I was going to accept either answer for this. Because this is one of those cases where order n is...
Or n being like whatever, like where you're trying to put it.
Correct.
Oh, yeah, I don't remember the average, worst.
Well, here's the thing. For the purposes of like the loosely speaking sense of these operations,
And it would choose the same order.
you can drop this term because as you keep growing bigger, the fact that you divided by 2 doesn't mean very much.
It's still linear.
It's still linear.
But is n the length of the list, or n is the position that you want to put it at?
So this is for the average case for putting it somewhere randomly distributed throughout the list. So it's the
Okay,
order.
but not at the n position.
That's worst case.
That's where,
Yeah, so for putting it at, so this would be the averaging, where the list is length n, and you're averaging over all possible positions of placement. But because these are just some kind of some coefficients to tell you kind of like how big this n term is, generally speaking, in a loosely speaking sense, you drop them. But it is important to know kind of about the strictly speaking sense as well. So thinking about both and kind of keeping both in your mind is important. You should double check yourself. At the same time, we'll do a lot of things where we talk about kind of the loosely speaking sense, the kind of big O sense of like, is it linear, is it polynomial, or something else. And so what's the worst case? We knew we wanted to just put it all the way at the last position, and all we knew was the front list?
isn't it just the same as the average, if you're talking about the loosely speaking case?
Yep. And the difference is that in the strictly speaking case, it'd still be order n. And so this is some time where the average is different than the worst case. If you're just kind of talking about it loosely, you say it really doesn't matter because they're all going to grow linearly. But if you get down to the nitty gritty, there can be times where that difference can matter. And we'll see some few of those later in the classes.
Are they all multiplied by 2 because you have to check if the next pointer is null?
Yeah.
We check if the next one.
Say if it's
Yeah.
the end, because at the
Depending
end it's
on how
not
you set
gonna
it up.
point to anything, and so you, unless you, then you just like drop off. Unless you knew that you were gonna drop off and then you'd add something.
Yeah. Or if you knew that you were never going to drop off the end of the list.
Yeah.
So we'll talk through that. Okay. It's a good one. So did everybody follow kind of talking through how going through every step was actually 2 operations? People follow that? How you had to like both take the next step and then decrease the count of how many steps you were trying to take? Does that make sense to everybody? Okay. Imagine a case where you want to find the 10th item in the list, but you don't know how long your list is. What happens if your list is only 3 items long and you try to go to number 4?
There's no reference.
Yeah, it's no reference, but I mean, your program doesn't know that, it just sees some location. And if you try and follow it, you just
Well,
say
why would
that.
there even be a next?
That's a good question. So, what are these things? And this gets back to a case of how would we represent this in Python? Does anybody have an idea how you would represent this in Python or some other programming language? Kind of hard to do it in that one. No, it's my apologies. Yeah, yeah. Thank you. So, can anybody think of how you might hold a list item in Python?
Someone in the dictionary or something.
Okay, a dictionary, you would,
Well, the dictionary, I thought
Or
ordered up the
dictionaries.
card.
Right, so you have a dictionary of the keys are, not, or the key value, so the value might be the reference to the next location you want to go to.
so one way you could do it is you could have a set of dictionaries where every item is a dictionary and it has one dictionary key for the data value and one for the next. And so you could have and so you could have a bunch of things like this. And so
Wait, so pretty much anytime you nest anything, pretty much anytime you're nesting, you're just making a linked list.
yep. And so what we're going to talk through next time is actually how you take this the next couple of steps. Because in this one, anytime you're nesting one thing inside of another, you're making linked lists. If you start saying, well, we're going to have 2 next pointers instead of 1. We're going to have a left pointer and a right pointer. All of a sudden, you've made a tree. If you start saying, a binary tree, if you start saying, we're going to have like 20 references or some large number, and they start going in circles, you've created a graph. And so from this simple idea, where all we're doing is kind of changing this, the assumptions about what the references are for the next item, you can get different data structures that are going to have different properties, which we can talk about. But a detail about, is this color better at all? Or is it still
I think
going
I
to
was
see?
just about to say.
Alright, well, let me know if I need to switch colors again, anybody?
You should try brown.
Drive around? Good, thank you.
It's so clear now.
Maybe you should move. So there's another way to do this, and this is actually almost getting to an implementation detail in Python. We're going to make an object. And this object is going to have 2 things in it. It's going to have, let's do this one. And so, can anybody read that at all? First of all, it's a good question.
So,
Yeah.
Suppose,
So this is, so two things I'm going to say about this. One is that it's kind of hard to read because I just read really low. And the exact reason why I gave you the set of examples where I've already written this out. I'm pretty sure this is exactly the definition that I wrote online. So if you were wondering and want to take a look at something, you should look at that notebook because it'll have this written in a legible fashion. And so yeah, I encourage you to look at those. Yeah, so this is the idea, and exactly that kind of one that Francisco was talking about. Linked lists, you don't really think about making in this kind of abstract way where they have kind of one on top of the next. But anytime you say, oh, I have some piece of data, it knows where other pieces of data are nearby. You're essentially building some type of linked list. It might be a more complex version like a graph, but that's what you're doing. You're building something that stores data and something that stores things that are next to it. And they'll all have the same types of general issues with each other, and some of the same general strengths as well. And that'll become more clear as we see those other data structures, I hope. And one last thing. Does anybody know how these data members, so the self.data or the self.next, are actually stored in Python? Every class contains a dictionary of all of its data members. And so these two things are almost equivalent. They're not, but they're very close.
So these like hash tables are found in objects.
Yep, we'll get there soon. How's everybody doing? My guess is that's probably about where we're going to end for today. And so now would be a good time to ask questions.
You mentioned links to the website. Where's all this stuff online?
Do you have the email that I sent at the beginning? There should be links in that to both this document and the
I
IPython.
didn't get an email with those things.
Okay. Send me an email, I'll send you it again.
You have sent me an email for the class, just not this.
Yeah, it should be in
I
there.
think it's in that one here too. They're not like at the top. They're kind of embedded in the text.
Sorry, I thought I meant to copy them down at the bottom of the two hyperlinks, or like the actual strings. Sorry about that.
Is there a situation in which you could imagine using a linked list would be beneficial for, like basically, you know, I could see, so one of the like pros that you listed is basically that you just don't need contiguous blocks of memory. Is there like a practical situation in which like you would actually implement a linked list where like, you know, you would be implementing it not for the random access and not for the insertion benefits, but for the contiguous block of memory benefit?
For the lack of a contiguous
Yeah.
block of memory? Yeah, you would. So let's say, I don't think it happens as much anymore, but do you guys remember like when hard drives used to get fragmented?
Well, yeah, see, so that's what I was thinking, but like nowadays, like, what would you ever use this for, like?
Yeah, so you can still fragment your memory space. And so if you kind of create a bunch of things,
What is fragmenting your memory
okay,
space?
good point. So,
I mean, I've heard people say that.
yeah. Um, Your computer has some block of memory. This is a thing called a heap. If it's program or space your computer can just request. And you would say, aha, I want like a block of memory from the heap. I want another block of memory from the heap. I want another block, and I'll take a really big block now. And then, you know, I ran out of memory. I can't ask for another big block like this big. There's just not enough room anywhere in my memory. And so you say, well, okay, I got to go back and delete some variables. You know, I didn't really like this one. I didn't like this one. And so I got space. If you type in the memory command in MATLAB or something, it'll report that the total amount of free space you have is big enough to fit your variable. But this variable doesn't fit here, doesn't fit here, and doesn't fit here. So you can't make this variable unless you can break it up as a linked list. If instead of one big long thing, this is 100 tiny things, you can scatter those out to this entire thing anywhere you want.
Right, but is that actually implemented in like anything?
Anytime you create nested structures that use references,
Yeah.
it automatically happens. We can ask though, is it a good thing? And so this is kind of getting into a more advanced question. Does anybody know how caches work in CPUs? No reason you should. At least that doesn't. And so you have your CPU, which is this tiny little block of processing power. It does everything. Like everything, almost every instruction your computer runs happens in your CPU. And so that means all the data that you want to run instructions on has to get to your CPU. And you have some big block of memory. Let's call this your RAM. And like, let's say you want to get some data from here. It unfortunately takes a long time in computer time for things to actually go all the way from your CPU to your RAM. It just takes time. And so part of that is because they're physically located further away from each other at the level of how fast computers are these days. So if you put a little piece of memory right next to your CPU, it can run faster. The problem is this is really hard to do without breaking it, and so they can't make them very big, otherwise they fail too often. And this is called a cache. And so your cache stores little cache-sized pieces of main memory so that your computer doesn't have to go very far.
What do you mean cache-sized pieces of memory?
So let's say your RAM is like 10 gigs of your computer. Your cache might be like 512 megabytes. And so it's a lot smaller than your RAM, but it's really close to your CPU. And so you can do things back and forth from your cache to your CPU really fast. But if you have to go to your, and so let's say cache to CPU takes 10 nanoseconds, like 10 milliseconds. So if we do RAM to CPU, it might take 100 milliseconds. And so then you can start saying, like, oh, like, I didn't manage to find what I was looking for in the cache. I needed to go look in main memory. It takes 10 times longer to do. And so now you can get this thing where you want to structure all of your data so that it fits inside of the cache. And people have actually gotten to the point where they start optimizing algorithms to make sure that everything fits inside of the cache. Because otherwise you have to keep going to main memory, which takes a longer amount of time. And it actually makes a big enough difference on computers these days.
So they basically just create linked lists limited by like the size of the cache, so you're just constantly moving things back and forth.
Yeah, that could be one way to do it. The most realized implementation of that is actually in databases for B-trees. And there it's more that your hard drive has a somewhat similar structure or similar costs to it. And so it does pages of hard drive space, store lookup tables for everything else down the road.
So just to make sure that I understand, this is, when you're talking about distances, you mean like literal physical distances?
Physical distances.
Okay.
This is actually physically closer to this,
Okay.
and that's part of why it takes less time to get stuff from it.
So
And
like
it
just
actually
make
makes
that
a difference.
closer to that.
So that's the thing. People keep making caches bigger and bigger because they want to get close to the size of main memory, like RAM, but it's really hard to do.
Why?
Because at this point you're fabricating things that are really small, and like you are getting to the size of quantum effects actually messing up the production. We're on like the order of like, I mean, architectures for computers are like 14 nanometer architectures I think they're working on right now. And being able to reliably produce caches in that same kind of size and space, and limited by different size. The issue comes down to that if you make a mistake anywhere in the cache, it destroys the entire chip. So you have to throw out the whole thing. And so people want to find some regime where they can make caches as big as possible with throwing away as few chips as possible. So it's this kind of trade-off between how big can you make the cache before it gets too likely to have some error, it gets somewhere that destroys the entire chip. So those are kind of the trade-offs for it. I admit, I'm not a hardware person, so I don't know all the details, but that's kind of the trade-offs there.
Thanks, Frank.
Yeah. That said, you don't actually need to know this for it's just a good bit of information. So, there's one thing I wanted to get back to in this linked list example. What are some ways to make a linked list, say, better for different types of operations? Let's say, instead of, let's say we're going to make a list where we're never going to care about what the item was at the front of the list. We're only going to care about stuff at the end of the list. How we can change the list. So we want to have order one time to find the last item in the list, and to add an item at the end of the list.
Perhaps previous. Start at the end and have reference previous.
Way too easy. Alright. Yes, that would be the correct answer. So if what we care about is the end of the list all the time, it doesn't do us any good to track where the beginning was. So instead we're going to say, let's just keep track of where the end is. But then you also made the other jump of,
Isn't the end hard to keep track of, because it's more likely to change?
okay, so that's the thing, we changed the end. What do we want to change now?
The change.
Yep, that's part of it. But what do you need to know to be able to find, okay, sorry, good question. What if we delete the last item of the list? Sorry, that's what that's right.
It's not.
So you already know the answer.
Yeah.
The second to last.
Yeah. And so, how do you know the second to last?
I don't know what that was.
Is there a better way to do it? If we don't care about anything?
If you're allowed to create references that go previous.
There you go. So instead, if you only care about stuff at the end of the list, instead of storing a pointer to the next one, store a pointer to the previous one. You'll never be
If you're
able
gonna
to.
just do it like that, why don't you just change
Doesn't
the
that just
order
get you
of the
back where you
list?
started, theoretically?
Yeah, they're equivalent. So this is
Well, I think the idea is that it's arbitrary, that the direction of the list is not, it's something that you set up by the structure of your items. So it's like, so you could easily flip the order if you decide that that's useful to you. You just have to change the root and then change all of the references, and then you just flip the direction, essentially.
Yes, yeah, so a lot of it's,
Right, I'm saying, why would you have a thing that goes to the end and goes back, instead of just changing the order of the list and then going forward?
so that's what they're equivalent, entirely equivalent. Like, if you changed all the words, like took off all the labels, they'd be exactly code
So
equivalent.
take extra space to, can you have references both forward and backwards? But I guess it takes twice as much space.
There you go. And so that's the thing. Sometimes it's exactly what you want. Like if you want something where like, let's say you've got some big circle and you want to move around the circle, like you can make some circularly linked list and you can just keep going. But if you want to go forwards and backwards, you need to have pointers in both directions. But